Yesterday, we learned 5 new terms. The first term we learned was electric potential energy. Does anybody remember what that means? Think about gravitational potential energy if you don't. What that meant, what the general definition of gravitational potential energy was, not the definition that we used last year, but the more general definition. Make that translation to electric potential energy. Is the energy stored in the system of 2 charges a certain distance apart? Just like gravitational potential energy really should have been the energy stored in 2 masses a certain distance apart. We simplified it a little bit last year, and we would still, for the most part, use that simplified definition of the energy stored in an object due to its height, because usually that object is so small compared to the other object, compared to the Earth, compared to the whatever planet the object happens to be on, that it doesn't really matter. Okay, the bigger object doesn't really come into play there. So we say it's the energy stored in the object a certain distance above the planet. We really should say it's the energy stored in the system of the planet and the object. This is the energy stored in the system of these 2 charges a certain distance apart. Well, the electric potential energy difference is not much of an extension from that. The difference in electric potential energy, if energy, by the way, is E, then electric potential energy difference would be delta E. Is there another term that's like delta E that means the same thing as delta E, or the change in electric potential energy? Work, good. So we're going to say not only is electric potential energy difference delta E, but we're going to say it's equal to W as well, which stands for work. W is also equal to what, though, besides delta E? Michael? Good. F times delta D. That's a physics 20 thing, really, right? Well, next we talked about electric potential. Pretty small difference between those 2 terms, at least in terms of the words. Electric potential energy, electric potential. Remember our analogy yesterday? We said that, I think we said there was 15 people in the room. What do we say? We had 45 bucks or something like that? Was it 100, did we say? Okay, let's change it. If there's 15 of us in the room, okay, then we're going to say we have $60, okay? The total energy would be 60, right? It's not amount that each of us have, it's the total amount. The energy would be 60. What's the energy per person, or the amount of energy per coulomb of charge? 4, right? And we take that, we find that by saying the total amount of energy, or the total amount of money divided by the number of people. Electric potential, which is a capital V, is the energy divided not by the number of people, but the amount of charge that you have. Electric potential difference is delta V, because of course if potential is V, then potential difference would be delta V. And we can find that by saying VF minus VI, because anything difference is final minus initial, right? But we can also find that by saying delta E over Q, right? It's final minus initial energy over the charge. It's like saying, look, we go to 7-Eleven, we got 60 bucks total. The 15 of us have $60. We go to 7-Eleven, we buy a Slurpee, okay? We come home with, let's say we come home with $15 total. We went with $60, we come home with $15 total. Got it? What was our potential energy to start? 60. What was our potential to start? 4. What was our potential energy to finish? 15. Okay. What was our potential to finish? 1, right. Total potential energy, 15, divided by the number of us, or the amount of charge that you have, which would be 15. 15 divided by 15 is 1. What's the potential difference? What's the potential difference? If we all had 4 to start off, and we all had 1 to finish off, the potential difference would have been 3, right? What was the potential energy difference? We went from 60 to 15. The potential energy difference was 45. The potential difference was 3. Now, you can find that potential difference in two ways. We could say, well, the final potential was 1. The initial potential was 4. The potential difference would be minus 4 volts. Or we could say the change in energy, well, we went from 45 to 15. Is that what I said? Yeah? Sorry, what did I do here? 1 minus 4 isn't minus 4, is it? When did 1 minus 4 become minus 4? Okay. In the bizarro world, 1 minus 4 might be minus 4. What is that? Negative 3. Sorry, our initial energy was 60. So we're going to say 15 minus 60 divided by 15. The final energy minus the initial energy divided by the number of people, or the amount of charge that we have. 15 minus 60 divided by 15 is going to give me minus 3. So whatever way you look at it, the final potential minus the initial potential, or you can say it's final energy minus initial energy divided by the charge. Potential difference. All right? Yesterday we left off with defining those terms, and then one more term that relates to units for energy. The standard unit for energy is the joule, but we sometimes use another unit called the electron volt. The electron volt is defined as the energy that we gain or lose when an electron speeds up or slows down through a potential difference of 1 volt. So, look, an electron, if it speeds up, it must gain a certain amount of energy. If it slows down, it must lose a certain amount of energy. If it speeds up or slows down through a volt, then the amount of energy that it gains or loses is 1 electron volt. Now, good news is, they give me the conversion factor for an electron volt on my data sheet. On the left-hand side of that data sheet, it says 1 electron volt is equal to 1.60 times 10 to the minus 19 joules, not coulombs, joules. We ever want to convert from electron volts to joules? Set up a little ratio. Okay, we got a situation where maybe, I don't know, maybe you're given 4 electron volts. You want to convert that to joules for whatever reason. What we're going to do is set it up as a ratio and say 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. And then we're going to say 4 electron volts equals x joules. The x goes up by multiplying. The 4 goes down by dividing. The 1.6 goes up by multiplying, I should say. And we end up with a value there of 6.4 times 10 to the minus 19 joules. So we just converted the electron volts to joules, right? Which is it's a conversion that you're going to have to do fairly often. The one that you'll have to do a little bit less often is the other way around, converting joules to electron volts. Let's say we got, let's make it 3.2 times 10 to the minus 18 joules. And we want to convert that to electron volts. Same ratio, 1 electron volt is 1.6 times 10 to the minus 19 joules. But this time we're going to say x electron volts is 3.2 times 10 to the minus 18 joules. X is going to end up being 20 electron volts. I mean, guys, listen, this doesn't just apply when you're doing this conversion, right? Set up a ratio for any conversion that you have to do. Remember on your momentum assignment way back here a few weeks ago, you had to convert pounds to kilograms. You remember that one? Or was it pounds to newtons, I think it was. Pounds to newtons? Okay. I don't remember for sure exactly what the question was. Remember though, it was a context of space and Mars, and it's talking about how these NASA scientists forgot to convert to metric. You guys remember that question? Yeah, we're doing a conversion like that where we're told maybe 1 electron volt is 1.6 times 10 to the minus 19 joules, or 1.6 pounds is equal to 1.0 kilograms. Okay. Set up the ratio. Okay, 1.6 pounds, 1.0 kilograms equals X pounds over 70 kilograms. Okay? My mass is 70 kilograms. How many pounds do I weigh? Okay? All we have to do is set up the ratio like we did with electron volts and joules. All right? That's just a little aside. Let's do an example question here that relates to those terms, including the electron volt that we've just used. Page 565, it says, moving a small charge of 1.6 times 10 to the minus 19 coulombs. All right, that's a small charge. That's the smallest charge we can have, right? That's the elementary charge. This could be an electron or a proton, or it could be some ion that just has that charge. It's moved between two plates that increases its electric potential energy by 3.2 times 10 to the minus 16 joules. Here's a question for you. If it increases the potential energy by that value, then it must have decreased something else by the same value. What did it decrease? If it increased the potential energy by 3.2, it decreased the blank by 3.2. Oh, come on, you guys are smart. You know the answer to this question. We haven't learned it yet, but you still know the answer to this question. Well, we haven't learned it in physics 30 at least. If you increase the potential energy by 3.2, then you must therefore have decreased the kinetic energy by 3.2, right? So in other words, this thing has slowed down. If it's increased its potential energy, it's like when I throw the pen up in the air. As the pen goes higher and higher and higher, its potential energy gets bigger and bigger and bigger. What happens to its kinetic energy at its speed? It gets smaller and smaller and smaller. Determine the electric potential difference between these two parallel plates. All right. This is a potential difference, potential energy. It's one of those problems involving those terms right there that we learned yesterday. If you keep your terms straight, these questions tend to not be very difficult. What do we got here? We got a charge. What else we got? What's that? Increases its potential energy. What variable is that? Is that V? Is that delta V? Is it E? Is it delta E? A, B, C, or D? V, delta V, E, or delta E? A, B, C, or D? Sorry? It's not just E. No. Okay, you're close, but it's not just E, Chantal. It would be delta E, right? If it increased its potential energy is a certain value, E. Its change in energy, or the increase in energy, or the decrease in energy would be delta E. So we're going to say delta E is 3.2, the difference between the initial and the final. We want to find the potential difference. V or delta V, potential difference. V or delta V. Tony? Potential difference. Big word in there, right?
Delta.
Good. Delta V. So what are we going to use here? Probably this one, right? The one that appears on my data sheet. Delta V is equal to delta E over Q. Delta E is 3.2 times 10 to the minus 16, and Q is 1.6 times 10 to the minus 19. Gives us 2.0 times 10 to the 3. Units, hey, what are the units here? There's two sets. You give me one of them, please. Michael, what's one? Volts is one, yeah. That's the harder one because it's not up in front of staring us in the face, literally. What's the other one? Joules per coulomb. So 2,000 volts, 2,000 joules per coulomb, they mean exactly the same thing, right? No electron volts there yet. It's coming, though. All right, let's have a short look at two questions on page 565. We'll take a look at them as a group when you guys have finished them. All right, if we're okay with that, let's take a look at one more problem here. Page 566. This one looks a little bit more complicated. We'll see if it is. It says a small charge of 3.2 times 10 to the minus 19. This is twice the elementary charge, right? This could be an alpha particle or another ion that has twice the elementary charge. It's moved between two parallel plates from a position with a potential of 2,000 volts to another position with a potential of 4,000 volts. We want to know the potential difference, and we want to know the potential energy gained by moving the charge. Take a step back from this for a second. We're not trying to solve this question yet. Okay, let's just take a look at a different aspect of this question here. Okay, We've got a positive charge in between two plates, a positive and a negative plate. What's going to happen to that charge? What's going to naturally happen to that charge? Where does it want to go? Yep. It wants to go left, right? Okay. If it goes to the left, what's going to happen to the speed of that charge? It's going to increase. It's going to get bigger, right? If you've got a car naturally wanting to go down a hill, what happens to the speed of that car as it naturally goes down the hill? In the absence of braking forces and in the absence of an engine, what happens to that car? Speeds up, right? But this is going again. This is going the other way, right? So what's going to happen to this thing as it goes the other way? Bryce, was your head up? What's going to decrease? Good. It's going to slow down, right? Its speed is going to decrease. It's like the car going up the hill as opposed to down the hill. And that requires work, right? We got to do work on this. There's a change in potential energy. There's a gain in potential energy in this system like there is when the car goes up the hill when we do work on it. All right. Let's find the potential difference here. Delta V can be found in two different ways, VF minus VI, but it can also be found by saying delta E over Q. Looks like, I think for question A, we're going to use the easy equation. Unfortunately, the one that doesn't appear on our data sheet, but the one that we're probably not going to have too much trouble remembering here. The final minus the initial is going to be 4 times 10 to the negative 4 times 10 to the positive 3, subtract 2 times 10 to the positive 3. And that's going to give us 2.0 times 10 to the 3. And we're going to say volts, or we're going to say the other unit we could use is joules per coulomb, like it was before. Now, what's the potential energy gained? We know there's potential energy gained, right? Hey, if it's not speeding up, it's slowing down. And if it's slowing down, it's like the car when it's going up the hill, not down the hill. And when the car goes up the hill, it gains potential energy. How much potential energy is gained here? What variable are we looking for there? E, delta E. Good. We're looking for delta E. So let's say, look, we got delta V. We just found it. Looking for delta E. Let's say delta V is equal to delta E over Q. We're going to rearrange that now, though, to solve for delta E. Q goes up by multiplying. It becomes Q times delta V. Q was 3.2 times 10 to the minus 19. And delta V, we just found, was 2 times 10 to the 3. That's going to be in joules, right? Because we're using standard units through this problem. We're going to get standard units for our answer, which is joules. But you can see there we want to convert that to electron volts as well. For whatever reason. I don't know, maybe electron volts is more convenient here. It's better here for whatever reason. On our data sheet, it tells us that 1 electron volt is 1.6 times 10 to the minus 19 joules. We want to find out how many electron volts is 6.4 times 10 to the negative 16 joules. 6.4 goes up, and we divide 6.4 by 1.6. X works out to be 4.0 times 10 to the 3 electron volts. Does that make sense? Does that conversion make sense? All right, we'll give you a couple minutes here now to work on these two questions on 566.